Commencer avec le. Sorry, we are going to. It reminds me that the first two speakers are French, and really, I apologize for that. We really did not even realize it with Philip, so there was no intention behind it. So the first speaker will be Jean-François Le Gall from for the University of Orsay, who is going to speak about maps and. Well, actually, what is your title?
I will show it in a minute.
I was not given the title. Okay, the continuous limit of random planar maps.
Okay, thank you. So I first would like to thank Bertrand and Philippe for the invitation. It's always a pleasure to be back in this place. And let me start by showing you a simulation which is due to Gilles Schaeffer. So this is a large triangulation of the sphere. It's generated at random. I don't know exactly how it is produced, how it is drawn. You have to ask Gilles about that. But certainly the goal of my talk is to answer the question which is written there in red. Well, can we get a kind of continuous space which is the scaling limit of this object? Okay, so already if you look at such a large map, so it's a planar map, a triangulation, you can see certain things, okay? You can think that you have lots of irregular points of spines or thorns here, and you also have smoother parts of the map, and okay, so you expect that you can recover certain phenomena like this in a continuous model, okay? So this I will try to explain. Okay, so the precise title is this, the continuous limit of large random planar maps. And essentially I want to discuss an object which I'm going to call the Brownian map, and which will appear as a continuous limit of various classes of large planar maps chosen uniformly at random. Okay, so let me immediately mention that there is still a uniqueness problem which is unsolved. So I'm going to talk about the Brownian map, but in fact it's a possible limit. And of course, one believes that the limit is unique, but until now it's not yet proved, okay? So still one can prove a lot about this object, okay? So how will it be defined? It will be defined as a certain random metric space. I will say more about this in a while. And essentially in this talk I want to describe some recent results concerning geodesics in this metric space. So perhaps a word about motivations for this. I think there are many motivations for studying planar maps. Of course, initially, this is a subject which comes from combinatorics. It's a pioneering work of Turt in the 60s. There has been many other combinatorics papers about planar maps. And there are also some nice connections between planar maps and theoretical physics. I think it started with the remark that enumeration of maps is related to expansions of matrix integrals. So we heard a little bit about that in the previous lecture. And more recently, random maps have also been used as models of random geometry in the setting of what is called two-dimensional quantum gravity. For me, of course, there is also a strong motivation from probability theory. So the idea is to start from planar maps which can be considered as discretized surfaces, and to construct in the limit a kind of Brownian surface. So this is very analogous to what one does to construct Brownian motion as a universal limit of rescaled random path. Except that here you don't start with path, you start with maps with discretized surfaces. Okay? So you expect also in this setting to have a universality property of the limit. Okay? You should get the same Brownian surface starting independently of the details of the discrete model you start from. And there are also more geometrical motivations that I will not discuss. Okay? So let me give you the outline of the lecture. So Well, the first part I will give you, recall a number of facts about planar maps. I think many of you already know about that. And in particular about bijections between maps and trees. Okay? So I think this goes back in combinatorics to the work of Corey and Vauquelin, beginning of the 80s. The case of quadrangulations, this was studied in Gilles Schaeffer's PhD thesis. And the one I'm going to use is the very nice extension of Schaeffer's bijection, which is due to Jérémy Bouthier, Philippe Di Francesco, and Emmanuel Guiter, which applies, in fact, to quite general classes of maps. Here I'm going to concentrate on bipartite maps, but they have more general bijections. Okay, and roughly speaking, the idea is that once we know that there is a good bijection between maps and trees, well, we can try first to study asymptotic for trees. Okay, and this has been done for a long time in probability theory, and I will discuss what is called the CRT, the continuum random tree, which is a scaling limit of many classes of discrete trees. Okay. So this CRT was introduced by David Elders in the beginning of the 90s. Okay. And then I will come to the main subject of the lecture, the continuous limit of planar map, and we will see that while we can define the Brownian map, the continuous limit of discrete maps, as a certain quotient space of this CRT. Okay? So this is in one of my recent papers, and there is also a related work by Marquardt and Mokadem. And I will also explain how you can get precise information about this continuous Brownian map. Okay? In particular, you can compute its dimension, you can obtain its topology, and so on. And in the last part of the lecture, I will describe more recent results, which I've just put on arXiv, and including full descriptions of geodesics in the Brownian map. Okay? Let me just also mention that there are some related papers which also study geodesics in discrete and continuous maps. In particular, there is a recent paper by Miermont, who works with a slightly different continuous model. And there is a paper by Jérémy Bouthier and Emmanuel Guiter, which is concerned with, in particular, with enumeration of geodesics in large planar maps. I think Jérémy will tell more about this this afternoon. Okay, so let me start with discussing planar maps and their connections with trees. Okay, so as you already know, a planar map is a proper embedding of a connected graph in the sphere, in the two-dimensional sphere. I consider only planar maps here. I don't work in higher genus. Okay? And of course, this will always be considered modulo homomorphisms of the sphere, well, up to continuous deformation. So we are interested only in the shape of the map. Okay, so typically you have vertices, you have edges connecting some of these vertices, and you have faces of the map, which are the connected components of the complement of the union of edges. Okay, so the map is called the 2p angulation if each face has degree Tp, that is, it has 2p adjacent edges. And here, for instance, we have an example of the case p equal 2, a quadrangulation. You can check that each face has exactly 4 adjacent edges, including the external face. So remember, we are on the sphere. There is, in fact, no external face. Okay, and it's more convenient to deal with rooted objects. So this means that I have distinguished an oriented edge, for instance, this one here. Okay? So I call V of M the set of vertices of my map, and I introduce the graph distance. So the graph distance between two vertices is the minimal number of edges you need to cross to go from the first one to the second one. So here, for instance, the figures in red represent the distances from the vertices of my map from the root vertex. Okay, so for instance, this one is at graph distance 2 from the root vertex. Okay. So essentially what I want to do, I want to consider a planar map chosen uniformly at random. So I pick one map in this space M and P of rooted 2p angulations with n faces. So n is going to be large. I'm going to consider a planar map with many edges or many vertices. And I want to look at the set of vertices equipped with a graph distance as a random compact metric space. Of course, here it's even a finite metric space, so it's much more than compact. But I want to look at it as a random compact metric space, and I want to get a limit as n tends to infinity in the sense of the so-called Gromov-Hausdorff distance, which I'm going to define in a while, which is a distance which has been introduced in geometry for dealing precisely with convergence of metric spaces. Okay? So, in fact, I want to stay in the framework of compact spaces. So, to this end, I will need to rescale the distance. Okay? So, in fact, I'm not going to consider here the graph distance exactly, but the graph distance rescaled by a certain negative power of n. Here, okay? Of course, I need to do so if I want the limit to be compact. Okay? If you don't do that, if you don't rescale the distance, well, in the limit you will get an infinite lattice, okay? Which is also interesting. In fact, this has been studied by various people, such as Schramm, for instance, Angel, and Krikun, and others. Okay? But here, I really want to rescale the distance and to remain in the framework of compact spaces. Okay, so
You mean that A is not the 3.1/2 that one would expect from a smooth?
no, A is a quarter, in fact. I will explain that later. Okay. Well, it has been known for a while that you need to take A a quarter because the diameter of a planar map with n faces is typically of order n to the power a quarter. So this is the correct rescaling factor. Okay. So maybe I can remind you of the definition of the Gromov-Hausdorff distance. So this is a very simple and natural idea. Well, I guess you all know about the Hausdorff metric. Well, if you want to compare two compact subsets in a metric space ED, well, you define the distance between K1 and K2, the Hausdorff distance between K1 and K2. Well, it's a minimal value of epsilon such that the first compact is contained in the epsilon enlargement of the second one, and conversely. Okay, very simple and natural distance on compact subsets in a metric space. So now, if you have two compact metric spaces, E1 and E2, which are not necessarily embedded in a big metric space, say, you can still define their distance, the Gromov-Hausdorff distance between E1 and E2. So you do something very simple. You try to embed E1 and E2 isometrically into a big space, capital E here. And you just compute the Hausdorff distance between these embeddings, between phi1 of E1 and phi2 of E2 here. Yeah, you can you try to embed them in such a way that the embeddings will be as close as possible in terms of the Hausdorff distance. Okay, so you minimize over all choices of the set capital E and the isometric embeddings phi1 and phi2. Okay? So this has been used in particular by Gromov, but also by many other people. In fact, there are variants of this. There are variants for pointed metric spaces, measured metric spaces, which I need in this work, but I don't want to give too many details. Okay, so this is a way of saying that two metric spaces are close to each other. Okay, so just a little bit of mathematics still. You look at the space of all isometric classes of compact metric spaces, and one can prove that this Gromov-Hausdorff distance, dgh, is a distance. This stays capital K. And you get, in fact, a nice distance in the sense that K equipped with the Gromov-Hausdorff distance is a Polish space. It's both separable and complete. So it's not a very large space. One might imagine that the set of all compact metric spaces is very large, but in some sense it is not. Okay? So this is nice for the problem which I'm considering here, because essentially it's very convenient and natural in probability theory to study the convergence of very random variables, taking values in a Polish space. Okay, so here we have we have exactly this setting. We have this random metric space, this one here. I have rescaled the distance here, which is just a random variable taking values in this space capital K. And we want to study the convergence. Okay. So exactly in this form, the problem was stated by Oded Schramm in his plenary lecture paper at the last ICM. Okay. But the same idea already occurs in a less precise form in an older paper by Chassin and Schaeffer. So here I'm not going to deal with triangulations. In fact, you notice that I'm going to deal with bipartite maps. I'm going to look at 2p angulations, well, mostly for technical reasons. In fact, it's slightly easier to work, well, it's, I think, significantly easier to work with bipartite maps. But of course, one expects that the limit would be the same for triangulations. Okay, so let me now come to the main tool I'm going to use, bijections between maps and trees, which is how you can code a planar map by a tree. So I need to introduce two very simple classes of discrete trees. Okay, so the first one I think is very well known. It's a class of plane trees, or rooted order trees if you prefer. So it's, well, it can be defined in several ways. I like to think of a plane tree as a genealogical tree, of this form. You have an ancestor here, which I represent by the symbol empty set. It has a certain number of children, which I denote by 1, 2, and so on. Say here, for instance, 2 has 3 children, 2, 1, 2, 2, 2, 3, and so on. So I like to define my tree tau as a collection of all its vertices, each vertex being represented by a finite sequence of integers. Okay, so it's a subset of the set of all finite sequences of integers. And there are obvious conditions, which you can easily guess. Okay, so I have a notation here for the set of all plane tree with n edges. Script capital Tn. Now something a little bit more complicated, but not much more. What I call a well-labeled tree, it's a pair that consists of a plane tree, so the object I've just defined above, and a collection of integer labels, LU, assigned to the vertices of the plane tree. Okay, so I have the same plane tree as above. Okay, just the red thing here is just the same as this one. But in addition to the plane tree, I have now labels assigned to the various vertices. Okay, so what are the rules satisfied by the labels? Well, the label of the root is always 1. L empty set is 1. The labels are positive integers, and I also require that when you move along one edge, the label can change only by +1, -1, or 0. For instance, you have 1 here, you can have 2 here. From 2, you can go to 2, or you can go to 3, or you can go to 1. Okay. So this capital Tn is a set of all well-labeled trees with n edges. So maybe I can keep the definition here. Now, I come to Schaeffer's bijection. So here I'm looking, in fact, at quadrangulations. So the case p equals 2, I have a set of all rooted quadrangulations with n faces, and capital Tn is the object I just defined here. Okay, all well-labeled trees with n edges. Okay? And theorem says that there is a bijection between the set of trees, capital Tn, and the set of quadrangulations. Okay? And, well, if you just say that, it does not tell you much. It tells you only that you have 2 finite sets which have the same cardinality, okay, which you can check directly. But this bijection has many nice properties, and perhaps I will explain that on an example. But essentially, the labels on the tree become the distances from the root in the map. Okay, so the vertices in the tree are going to be vertices in the map also. And what was the label on the tree becomes the distance from the root of the corresponding vertex. Okay? So for instance, if you want to count how many vertices are at distance k from the root, well, you just have to count how many vertices in the tree have label k. And as I said before, there is just a slightly more complicated version, which is in fact the one I use for 2p angulations due to Boutier, Di Francesco, and Dieter. So maybe I will show you the bijection on an example, because this is really important for what follows. So in the case of quadrangulations, which is the simplest case. So okay, so I start here from a labeled tree, a well-labeled tree. So this is this object here, the blue tree, and the labels are indicated in red. Okay? And I'm going to construct a map, a quadrangulation. Okay? So what I do first, I redraw, in fact, the same tree. It's just the same tree in dotted lines. Okay? And I have put the same labels, of course, as here. And what I first do, I add an extra label, which I denote by partial d here, this one here, an extra vertex, sorry, which I denote by partial d, which is labeled 0. Put label 0 here. So that's going to be in fact, the root vertex in my map. And the other vertices are going to be the vertices of the tree. Okay, so how do you get the map now? Well, what you do, you do the contour of the tree. What do I mean? You start from the bottom of the tree and you go up and down along the edges like this, from the left to the right. Okay? And each time you meet a vertex in this evolution, you connect it to the last visited vertex with strictly smaller labels written here. Okay, so you start from the bottom. So you start from 1 here. Well, you have no choice. You have only one vertex with smaller label, which is the extra vertex I have added with label 0. Okay, then you arrive at 2. Okay, the last visited vertex with label 1 is this one. You arrive at 1. So 1, you have no choice. You connect it to this vertex with label 0. And then you go down this way, and then the last visited vertex with label strictly less than 2 is this one, in fact. So you draw an edge like this, and you continue this way. Okay, so maybe I can go faster now. 1 is connected to 0, 2 is connected to 1 here, 3 to 2, 2 to 1, 3 to 2, 2 is connected to 1, 1 is here, and 1 is connected to 0. No, so I stop. In fact, I stopped before the last return to the root. That's important. Okay, so if you look now at the red edges, which I have obtained here, well, you can check that this is a quadrangulation. Okay, this gives you a quadrangulation.
You need it bipartite because in a bipartite it's always plus minus 1 on labels, never 0.
Yeah. Mm-hmm. It's important to have a bipartite, for such a thing. Yeah. So you have as I said before, you have a nice extension of this to bipartite maps. This is only for quadrangulations, okay, for the moment. But you have a nice extension for bipartite maps. If you look at non-bipartite maps, it's more complicated. You still have some bijection, but it's more complicated. A little bit. So I should decide what's the root of the map. The root is the first edge here. Okay, you have drawn. And the important thing is what is written here, the fact that, well, the graph distance now in the map I have obtained, in the quadrangulation I have obtained, it's just the label I had before on the tree. Okay? For instance, this vertex here on the map, you can check that it is at distance 3 from the root vertex here, or this one is at distance 2 and so on. Okay, so this is a combinatorial observation. So now, as I said here, essentially the idea is just now to use asymptotics for trees, and then the bijection I have just described. So let me come to asymptotics for trees. So I remind you of the notation. So this was a set of all plane trees with n edges, script capital Tn. And what I do, I pick one uniformly distributed over this set. Okay, I just pick one big plane tree with n edges uniformly at random. And then you have the following theorem. So, well, I wrote it as a convergence in distribution here, but in fact, you can make the construction so that you have an almost sure convergence if you want. Okay? With probability 1, you have a convergence. So this tau n rescale, well, you equip it with a graph distance on the tree, rescaled by the usual factor 1 over square root of n. So I put a 2 here, it's not very important. This converges to some limiting object, well, which I will say a few words about it in a while. This TE here, so for the moment it's just a limit in the Gromov-Hausdorff sense, so it's just a random compact metric space. And this is a so-called CRT, continuum random tree, which can be viewed as a tree coded by a Brownian excursion. So maybe I can, so before defining this object more precisely, I can explain what in fact Aldous proved. So Aldous was considering the contour processes of the tree. So you have your tree, you do the same as what I was doing before. You do the contour like this, but you associate with the contour random function which gives you the distance from the root at each step here. Okay, so you have a function like this in the case of this tree here. So you rescale the contour probably, in a suitable way. So time steps are going to be 1 over 2n, and you rescale by 1 over square root of 2n in space. And then this random function converges to a Brownian excursion, okay? Which is a well-known random function in probability theory. So if you are not familiar with this, you can think of the Brownian excursion as a piece of Brownian motion starting from 0, ending at 0 at time 1, and conditioned to remain positive over the time interval 0, 1. Okay. So why is such a result interesting? Well, just a short parenthesis. Why would like one to prove that? But well, in fact, you can get a number of asymptotic distributions for discrete trees from this. Okay. So for instance, if you look at the height of the tree, so the maximal generation in the tree, well, the height of the tree, you can view it as also the maximum of the contour here. So because of this convergence, it will converge also in distribution to the maximum of the Brownian excursion after rescaling. So one knows explicitly this quantity here, well, in the form of a complicated series, but it's known. And so you get, well, for free, you get such a limit theorem, which was in fact known before Aldous' work, which was due to Flageolet and Odlyzko. But this is just to give you an example of the general philosophy. You have a big limit theorem for the tree, this theorem here, and you expect that you can deduce from this big limit theorem many asymptotics for specific functions, such as the height of the tree, but you can think of many other functions of the tree. Okay? So, of course, one would like to do the same for maps, okay, to have a similar big limit theorem for maps, and then to have applications to various asymptotics of the map. Okay? This is, I suppose, a little bit the philosophy of the work. So, now I want to explain a little bit what is this object here. So for this I need to introduce the notion of a real tree. So this is well known in geometry or in topology. And it's a very simple notion. What is a real tree? It's what you would imagine to be a tree in a continuous setting. Okay, so it's a metric space with the property. Here I'm going to look essentially at the compact case. Okay, a metric space such that if you pick any 2 points A and B in this space, while you have a unique arc, a unique way of going continuously from A to B in a one-to-one manner, in an injective manner. So there is a unique arc going from A to B, and this arc is isometric to a line segment. Okay, so you can think of this as just a union of segments like this in the plane. And of course, you have to put the right metric on this union of segments. It's not a Euclidean metric you put. You have to put the right metric so that you have these properties here. Okay. But of course, the object can be very complicated. It can have, for instance, infinitely many leaves, even uncountably infinitely many leaves, and infinitely many branching points. still being compact. Okay. Now, I explained a little bit very shortly here that plane trees, of course, are also coded by contour functions or dict path. In combinatorics, I guess people call them dict path. So there is a one-to-one correspondence between this object and these ones here. And this correspondence turns out to work also for real trees, okay? In some sense. In the sense that starting from a contour function, so a continuous version of this object here, you can define a tree associated with it. Okay, so this it means there are two ways of looking at the CRT, in fact. The first way is just to do what I have just explained. So you define it as a tree coded by a Brownian excursion. So what does this coding mean? I don't want to write down the precise definition because it's a little bit, it's not very complicated, but it's a little bit annoying.
Would it be in terms of a metric space with the metric and that's it?
Yeah, that's it. The metric space is just a quotient of the interval 0, 1 for a certain equivalence relation, and there is an explicit distance. But informally, what you say is that if you start from the tree, you imagine that you explore the tree like this, you do the contour of the tree as before, and the function that gives you the distance from the root is going to be the Brownian excursion. Okay? But this is informal, because you cannot, in the continuous setting, you cannot define the contour as we can do in the discrete setting. But still, you can do the other way around. You can start from this and define the tree. Okay. But maybe something more elementary, if you don't know about Brownian excursions, there is a simple recursive construction. So fix an integer n, and you pick n positive numbers x1, x2, xn, distributed according to this distribution. So you have a very simple density here. So there should be a constant here. It's not very important. Okay? So you have very simple explicit distribution. And what do you do with these numbers? Well, you start with the first branch here with length x1, and then you add a new branch with length x2, and you choose to attach this new branch at a point here which is uniformly distributed over the first branch. Okay? And then you continue. The branch with length x3, you attach it at a point which is uniformly distributed over the existing branches, and so on. Okay? Then,
So how do you choose left or right?
very good question. I wanted to say a word about it. Yeah, excellent. You choose left or right with probability 1/2. That's important because this is written in below. You see, I will need a lexicographical order on the tree. So I will need to know which vertex is before which one. Okay. So it's important to say left or right, and you choose it with probability 1/2 each at each step. Okay. Yeah. Okay, so this is, so here you have only a finite number of branches, but you can do it with n equals plus infinity. You put an infinite number of branches, and you have to take a completion. Okay. And then you get the same object as here. Okay, so just a different way of looking at the same object.
Where is the distribution coming from? Oh, just because of the length?
Where's the completion coming?
Where the distribution was coming from? The distribution. Where is it?
Oh, I will tell that later. Yeah. No, you cannot guess it like this. No, it's yeah. Well, these trees are limits of discrete trees, so you can get the distribution by passing to the limit from discrete distributions. Okay. So, but I don't want to explain that. So, in fact, in my setting, I'm interested in well-labeled trees. So I have labels in addition to the trees. So I need to assign also labels to vertices of a real tree. And if you remember, so where was it? Yeah, in my definition of well-labeled trees, the labels could change by +1, -1, or 0 when you move along one edge. So here in the continuous setting, you can see here that you have a kind of random walk. If you look at the evolution of the labels on an array starting from the root. For instance, you start from 1, you go to 2, you go to 1, and so on. So in the continuous setting, what you will have, in fact, labels will be Brownian labels on the tree. Okay, so given a real tree, capital T, So you always have a root which is a specified vertex. You introduce a Gaussian process. It's really, okay, it's really the usual definition of Brownian motion. You impose that at the root it's 0, and otherwise what you get that the variance of the increment between A and B is exactly the distance between A and B. Okay? So it's really Brownian motion indexed by the tree. Okay? So just a picture. It means that if you want to, for instance, if you want to define the label of a vertex A in my tree, you just have to run the Brownian motion, this red Brownian motion, over a time interval whose length is the distance from the root to A. Whose length is the length of this segment here. Okay. But of course, if you have a second vertex B, you take another Brownian motion, but it will be the same Brownian motion up to that level here. Okay, that's,
But you start from 0 and you cannot go negative.
it can go negative. Okay, so I have to. No, you're right. Yeah, I will come to that in a minute. This object is not the proper continuous limit of this, because here, of course, it becomes negative. Okay, Brownian motion immediately becomes negative. Okay, so you have to condition it in some way not to be negative. Okay, so this will perhaps what I'm going to explain now. So what is the scaling limit of well-labeled tree? Well, this is just to remind you the notation. This is just uniform over all well-labeled trees with n edges. So this is the tree part. These are the labels. You rescale the distances by 1 over square root of n as before. Or you can put a 2 here. I don't care too much about constants here. So rescale the labels. So you have to rescale the labels by 1 over square root of n. This is where the n to the power a quarter comes. Essentially because the height of the tree is of order square root of n, but then you move at a random walk on the tree. Well, if you move on the array of the tree. Okay, so typically after square root of n steps, the size of the labels are going to be of this order, square root of n. Okay. So if you do this rescaling, well, you get the continuous limit for my well-labeled trees. Well, it's the CRT I had before. And this object, there is a bar here. So it's not the Brownian motion indexed by the tree, not exactly this object, but you subtract the minimal value of this. Okay? And in fact, what you need to do, if you think of convergence of rooted objects, you need to reroute this one at the minimizing vertex, okay? At the vertex with minimal label. Okay. And already from this result, there are many applications to random maps, for instance, quadrangulations, but in fact more general bipartite maps. And there are also versions for triangulations, looking at the profile of distances from the root, for instance, or the radius, which is the maximal distance from the root. Okay, so this has been done by all these people in particular.
Question.
Yeah.
By this rerouting, does this produce a vector, or how should we think of that?
Well, I have not been so much precise, but in my notion of the real trees, there is a root which is a distinguished point. So here, essentially, here I have also a root. So I want the root here to converge to the root here. So the root that you need to get here is it has to be labeled 0. Okay, after rescaling, label of the root it has to be 0. Okay, so this is why the root is the only vertex in this object such that z bar is equal to 0. Just what I'm saying here.
When you do the process of adding one branch after the other,
Yeah.
are you changing the root
No.
an infinite number of times?
No, the root is fixed for the beginning. It's
In this rerouting, I mean.
Oh, in this rerouting, you mean? No, here I construct the full object, but then I change the root here. I construct the full object, this object here. I construct these labels here. These are the continuous labels, this z bar. And I decide that the root is the vertex with minimal z. That is the only vertex such that, if you want the root is such that z bar at the root is equal to 0. Okay. Okay.
But you know it's unique.
You have to prove it. Okay, so let me come to the continuous limit of maps. Okay, so So I remind you of the setting. So it was a set of all two triangulations n faces. I pick one Mn uniformly at random in this set. So V of Mn is a set of vertices. dgr is the graph distance. So you look at this object, the vertex set equipped with the rescaled graph distance. So this is just a constant. This is the rescaling as you can get, well, you can get from the, remember that in the bijection, labels were corresponding to distances from the root. So you had to rescale labels by this factor. So it's the same factor you need to put here, of course. Okay?
Excuse me.
Yeah?
Can you remind us, in this bijection, did it have to be a tree with a given planar embedding, or was it an abstract tree?
Oh, it's a tree from. No, there is no special planar embeddings. In the bijection, you mean with discrete trees, it's really a plain tree. Okay.
Yeah, it is. Therefore, it is an embedding. It is embedded.
Oh, yeah. It is an embedding. Okay. But okay, it depends what you call an embedding. Yeah.
You forget the embedding here?
No, because there is a cusp of left and right.
Where do I forget the embedding?
When you say vertex set, comma, distance,
Vertex set.
comma, distance to the root.
No, I have my tree. I just look at the set of vertices. I view it as a metric space. If I put a distance on it, yeah, okay. I don't care about the embedding at this point.
It depends how you were changing this, how you were choosing this left and right.
That's important in my discrete setting. Okay. I deal with plane trees where you're right. I have an order in plane trees, left and right. Okay, but that's the object you need to consider to have the bijection with maps. Okay, and but now if you want. Okay, that's just a map. Okay, this theorem makes sense even if you don't say anything about trees. I'm not considering trees there. Okay. Just dealing with maps. Okay, so you get. So if you remember, okay, I have to say two things first. Important thing. You see, I have to take a subsequence of values of n because this is related to the lack of uniqueness I mentioned on the first slide. Okay. There is a compactness result, but you are not sure that the limit is uniquely defined. Okay, so of course, when I think most people believe that there is uniqueness of the limit. So this should not be necessary, this subsequence. Okay.
But this is because of the proof technique.
Yeah, it's a problem. It's a problem that I cannot characterize. I will say more about that. I cannot characterize exactly the distance. You cannot characterize exactly this capital D. You can say a lot about it, but you cannot characterize it. But you say that you know that the space will always be this object, which is essentially the CRT, the one I had before, but with certain vertices identified. So you need to take a quotient with a certain equivalence relation. Okay? You have to identify certain vertices of the CRT. Okay? So how do you identify these vertices? So this is explained below. Well, to identify the vertices, you need these Brownian labels, which I call Z. Well, in fact, I shift the labels. So to have positive labels, I do exactly the same as before here. I define Z bar, which is ZA minus the minimal label. That's very important. And then the equivalence relation is defined in this way. You need to identify two vertices A and B if they have the same label, but also if between A and B, all labels are larger than the label at A or at B. Okay? So Z bar A is the same as Z bar B, is equal also to the minimum between A and B of the labels. So what does it mean between A and B? So here it's very important to have this notion, somebody asked the question, of order on the continuous limit. You have to define what is the lexicographical interval between two vertices A and B. So it's the same as in this discrete setting. You have vertex A here, vertex B here. You go from A to B following the contour of the tree. You can make sense of that. So you want all the labels of the red vertices here to be larger than the label at A, which is the same as the label at B. And the thing I don't exactly know is the distance D. Well, still, there is something very important one knows, is that capital D is a distance on this quotient space. And there is also the same property as in the discrete setting, meaning that the distance between the root row and the vertex A is equal to the label of A. So you don't know D so well, but at least you know the distances from the root. This is just obtained by passage to the limit. Okay? In the discrete setting, we had something similar.
So this identification comes from the fact that the root goes to a different place?
No, I explain you why you have this identification just now. Okay? So
now again, the root, so the uniqueness of the root, that's also almost surely.
sorry.
The uniqueness of this root, that's almost surely.
Everything is almost sure. Yeah. Yeah.
Can we think to the uniqueness factor as the fact that in the true triangulation you have a degree which is about the 1, so every rescaling by 1 over n to something is making the degree essentially 0, so the nearest one over 0 is a single vertex.
Yeah, I don't know. And I'm not sure. We can talk about it if you want. I don't know. So perhaps I explain you why we have this identification. Certainly, it comes from the discrete setting. In the discrete setting, when did you draw an edge between a vertex V and a vertex U? Essentially, when the label of U was a label of V minus 1, and when in between U and V, all the green labels there were greater than the label at V. Just remember, I showed you an example how you were generating the edges of the map from the tree. Okay? So this definition here is just a continuous analog of this property. So you will have such a property for vertices in your tree which are far away. So it means that they will be linked by an edge of the map, and in the continuous limit, it's going to be the same vertex. Okay. So this explains to you why you have this identification.
Now I'm confused a little bit because it seems to me that the vertices which are in between, they have a smaller distance.
No?
No?
No.
Where's the root?
The root is there, but the distance, you are confusing the distance in the tree and the distance on the map. The distance on the map is given by the label. So vertices in between here may have greater labels than the label here. Remember the labels, it could change by -1, so you can decrease there. Okay?
But the labels only tell you the distance from the root,
Yeah.
not the distance between 2 points.
That-
It's only a boundary.
Yeah,
This is the problem.
that's a big problem. Yeah. Yeah. So that's why you don't get easily uniqueness of the limit. Okay? But still, you don't identify so much points with this equivalence relation. You can check that equivalence classes for this. Typically, they contain 1 point, so you don't identify anything in that case. Or they can contain 2 or even 3, but not for many vertices. So you have this real tree, which is where you identify certain points, but not so many. So actually, a consequence of the theorem there is the fact that, for instance, the topological type of the limit here, even if you cannot characterize the limit because you need to take a subsequence, the topological type of the limit is uniquely determined. Okay, it's just this quotient space here with the quotient topology. You can prove that. But of course, there are still open problems. Okay, identifying D, or showing that, of course, one believes that D does not depend on P, so it should be the universality property. You should have the same limit here for many other classes of planar maps. Okay, so let me just state 2 theorems about the Brunner map, 2 things that you can prove. For instance, you can compute the Hausdorff dimension of the limit. You can check that it is almost surely equal to 4. And I think this was already in the physics literature, maybe with a different definition of Hausdorff dimension, but you can prove it precisely. And you can also characterize the topology of the limit. You can check that this quotient set here is in fact homeomorphic to the 2 sphere. Okay? So in a sense, it's not surprising because you start from graphs which are drawn on the sphere. You put more and more vertices. In the end, you get an object which is homeomorphic to the sphere. But still, you can think that what you are doing here, you are starting from a real tree, something which is very different from a sphere, something which is just a union of segments like this. Okay, you can represent it that way, and you identify certain points in this real tree, but not so many, and you get something which is homeomorphic to the sphere. Of course, this has also some combinatorial consequences. For instance, it tells you that in a large planar map with n faces, you cannot have a small separating cycle. By small, I mean of size smaller in comparison with the diameter of the map. Okay. Such that, of course, both sides of the separating cycles have a macroscopic diameter. So in the last 10 minutes, I want to discuss a little bit the structure of geodesics. This is the last part. So let me start with discrete maps. So say, for instance, quadrangulations. And I'm going to use this bijection between trees and quadrangulations I explained before. But you can do the same with 2P angulations using the bijection of Boutier, Di Francesco, and Gitter. So let's consider quadrangulation. So just fix one vertex V here in your map. So it's the same as saying that it's a vertex in the tree. And you want to construct a geodesic from this vertex to the root of the map. Well, so what you do, you remember how we generated the edges of the map. So we go backwards on the tree until we meet a vertex with the label of V minus 1. Okay, so we look at the last visited vertex with strictly smaller label. So this is the V prime which is there. So we have an edge like this. And then we go again. We do the same. Starting from V prime, we go backwards on the tree. And we arrive at V second. So it will be now a vertex with label L minus 2 and so on. So remember that the label corresponds to the distance to the root. Okay? And if you continue this way, well, in the end, you will automatically arrive at the root of the map. And you will get a geodesic from V to the root. Well, of course, you all know that geodesics are not unique in discrete maps. So why is there no uniqueness? Well, simply when you arrive at a vertex which is not a leaf of the tree, which has several corners, for instance, this one, you can choose, in fact, any of the corners to draw the next edge. I mean, you can decide that you just forget everything that is above, all the descendants, if you want, of this vertex. This is what I've done here. But you could also explore this part here and possibly draw a different edge like this. And you would get a different geodesic. Okay, so you have the choice of the corner corresponding to the vertex where you arrive. Okay? And in fact, in this way, you generate all geodesics from V to the root, but you have many of them because you have many choices, okay, because of this. Okay, so that's a very simple discrete observations, but in the limit, it's going to be exactly the same. So what do we have in the limit? So we have this object here, the Brownian map, root row. So I told you, you have this lexicographical order on the tree. You know the left from the right on the tree. That's very important. And you have these labels, D bar, which correspond also to the distance from the root to A. Okay, that's what I have written here. And now you do the same. You start from A. Now for every t between 0 and the distance between the root and A, you define this object phi A of t, which corresponds to the last visited vertex before A with label t. So you go backwards, if you want, in the tree until you get a vertex with label t.
Before it was t minus 1.
This is continuous now.
No, that was the scheme.
This is a continuous model. This one is continuous, the previous one was discrete.
Before it was important that you were starting from L and always reaching 0 because you were having minus 1. If minus 1 becomes minus 0, you never reach 0 anymore.
Yeah, these labels depend continuously on the vertex on your tree. So when you move on your tree like this, you explore it. Okay, you have a continuous function. The label is continuous function. You start from 0. You arrive at z bar a. You have to pass through any value t between 0 and z bar a. It's just how is it called in English?
Adding infinitely many zeros can give you a positive number.
Yeah, okay. Okay. Okay, so this is what I call a simple geodesics that are generated in this way. Now, remember in the discrete setting, we had the choice. Okay. We had the choice because we could choose the corner, we could go this way, or we could just go like this. Or now the point is that in the continuous setting, you can prove that this geodesic only visit leaves of the tree. So typically, you will have no choice because at leaves you have only one corner. Okay, except possibly, and this is very important. Of course, the starting point, the point A that you choose here, it may not be a leaf. Okay, so what happens if this is not a leaf? Well, if it's not a leaf, you have the choice. Well, my picture is not very good, I'm sorry. But you can construct several simple geodesics. They differ at the very beginning. So here's the point A, say, it's not a leaf of the tree. But you can choose a corner. You can start the first edge. You can draw it. Well, it's no first edge. I should not say that. But you can really define a simple geodesic going this way around. So it's going to explore first the descendants of A, possibly, and another one which ignores the descendants of A in the tree. And eventually, they will merge, in fact, at some point from the definition. But you have typically when you have a simple point of the tree. Well, a simple point which is not a leaf, okay, you can have two geodesics. And when you have a branching point, you can even have three because you have three corners in that case. And I didn't tell you, but it's easy to prove that 3 is the maximal multiplicity of the tree. Okay, what I call multiplicity, the multiplicity of a vertex is just the number of connected components you get if you remove the vertex. Okay, the usual notion.
And the volume of the bubble remains of order 1 in the limit.
The volume of
this bubble that you have starting from a 2 point. In
this
principle, making this scaling, this bubble could have shrunk it to 0, almost surely, something like that. But instead it survives.
Yeah, I'm not sure I understand the English. In fact, this barber.
Barber.
What is it?
Barber. That's something like this, but I also don't know where it's pointing to.
I mean, this diagram starting from A is a kind of lollipop in a sense. One can think that the circular region maybe in end will scale to 0, or it survives. Does it survive or scale to 0?
Okay, I will say something about the dimensions of that one gets. But okay, I'm not sure I understand your question. We can talk about it later. I just finish in 2 minutes. So the fact is that the difficult fact to prove, in fact, is this: that you get all the geodesics to the root in this way. Okay, so this is the theorem I wanted to state. So you have to deal separately with the leaves of the tree. So I call the skeleton the tree minus the leaves. Okay. So this is, in fact, a small set. The full tree has dimension 2. This one has dimension 1. Okay, so this one is much smaller. And now remember, you have to take this quotient. It turns out that if you look at the projection from the tree to the Brownian map, you identify certain points. In fact, you identify no points of the skeleton. Okay, if you restrict the projection to the skeleton of the tree, it's just a bijection. And the dimension of the projection of the skeleton is small, it's less than 2, whereas the full map has dimension 4. Okay, it's much bigger. Now the result is that essentially if you are not in this skeleton, then you have uniqueness of the geodesic. If you correspond to a leaf of the tree, there is a unique geodesic from the root too. On the other hand, if you start from a point which is in the skeleton, then you can you get several geodesics. You get exactly as many distinct geodesics as the multiplicity of the point in the tree. Okay? And this follows from the fact that all geodesics are generated in the way I explained before. Okay? And just maybe, just to conclude with perhaps some applications of these to discrete models. How can you use that now to get information about discrete models? So just the same notation as before. I have a 2p angulation with n faces mn. And you look at the set of all geodesics. Now I'm in the discrete case, okay? All geodesics between the root and the point x. I call this geo from rho to x. And what the theorem tells you is that for a typical point of the map, well, you will have a unique geodesic, but unique in which sense? It's a microscopic uniqueness. It's saying if you take any two geodesics from rho to x, they will be at distance less than any delta times n to the power quarter. So you will have uniqueness up to deviations which are small in comparison with the diameter of the map. Okay, so this is for a typical point. But you can also ask the question for exceptional points. So what happens is that, well, I define kind of multiplicity of a point x. Essentially, this is the number of distinct geodesics from rho to x. Distinct, I mean that their mutual distances are at most delta times n to the power quarter. Okay? And the theorem tells you that while the probability that you have a point with multiplicity greater than or equal to 4 goes to 0 as n tends to infinity, you cannot have 4 macroscopically different geodesics from the root to a given point of the map, but you can have 3. Okay? If delta is small enough, with a probability close to 1, there will exist a point x for which there are 3 macroscopically different geodesics. Okay, so these are consequences of the theorem I mentioned in the continuous setting. Okay, but I wanted to finish with these applications. Thank you.
There is something not very intuitive in your statement about the characterization of geodesics, is that you can never, if you start from a generic point that is a leaf of a tree, you never hit a multiple point, I mean a branching point.
Yeah, that's true, yeah.
So what is the explanation? Is there
well,
explanation for that?
there's something I wanted to say, that all these results about geodesics remain true if you replace the root with a typical point of the map. What I mean by typical, you choose a point at random. You have a volume measure on the object, so you can pick a point at random with a volume measure. So the theorem I stated, well, this theorem about the number of geodesics, they all remain valid in this way. Okay. Now it's true that you can have also exceptional points, and you can look at geodesics from exceptional points. And I think in your paper with Emmanuel, you have situations where you have truly distinct geodesic pairs of points corresponding to truly distinct geodesics. For me, this would be really exceptional points. Okay, I don't see that in my approach because I deal either with a root or with a typical point. Okay. So I don't know if this answers your question, but it's a different matter. Yeah?
Yeah, but even with a generic point, for me, it's not very clear that you cannot extend this multiple geodesic by some finite part. But we can discuss that.
We can talk about it, yeah.
If I understood correctly, this space is always homeomorphic to S2.
Yeah.
And so you have this metric which is random.
Yeah.
Is there any relation with at least conjecturally, with the functional integrals that people consider in physics?
With which conjecture did you say?
With the functional integrals where you integrate over all possible metrics.
Oh.
Is there any conjecture?
Yeah, I think that the hope is that you can, if you discretize surfaces, you can, in some sense, if you integrate over all planar maps of a certain type or triangulations, for instance, in some sense, you integrate over all possible metrics on your surface, but yeah, okay.
UV theory.
Yeah.
The UV
So it's related with UV?
supposed to be, yes.
Well, yeah, but nobody figured out how to fix geodesics in UV field.
Even the number 4, for example.
It's 4 postdoc dimension. Yeah, okay, that's understood from physics point of view.
I'm sorry, we interrupted you. You wanted to answer now this question?
No, it's. I think you've answered very well. Yeah.
Yes, we are in the famous Isaac Newton Institute. I made a study with April Twin. And my question is, did you get this intuition by looking at an apple leaf? In the leaf, you can see a map of the nervure and the underlying branching structure.
Yeah.
Both sides are geodesic. In the middle, there's a third geodesic. So did you?
No, not really. But it's a good picture, yeah. No, I didn't think about that. No.
Maybe you can go more by thinking of real leaves.
Yeah.
Any other questions?
Is there a table corner argument to understand why for more than 4 the multiplicity goes to 0? I mean, this 4 must be also the 4 of the Hausdorff dimension.
Oh, you mean the 4 which is there?
Yeah.
No, I don't think it's related to Hausdorff dimension. No. I don't see that. No. No, I think it's I see that in the continuous picture because you have points of multiplicity 3 in your tree, but not multiplicity 4. It's only a binary branching if you want in your tree. Well, that's a bad explanation. The way you get the result.
Another way of formulating the question is there a way of doing something to the model, to those trees, to the coding function, or something like this, so that you can go beyond?
Okay, so you can change dramatically the model if you put certain well-chosen Boltzmann weights on your maps. So you can force your maps to have very large faces, for instance. Okay, and this is work I've just started with Grégory Miermont. You expect to have a different continuous model then. Okay, to have a also described by a kind of tree, but a very different tree where you will have, in fact, different multiplicities. Yeah.
I'm asking this question because you have other regimes of quantum gravity when you start putting matter, looking at critical points, and you get other numbers than 4 in those cases.
Okay. Yeah.
Serious comment, it's in Laurentian quantum gravity. There's Catalan, dimension 2, the trees, and if you allow Bebe universe, then the limit is the Euclidean quantum gravity in the dimension 4. There's a relation between Laurentian quantum gravity is 2. If you allow Bebe universe, it's arithmetic 3. The limit, what I understand,
yeah, but this is pure gravity. That is, you don't put any matter in there.
But the limit you get dimension 4 without any matter.
Yeah, but if you start putting matter, then you modify things. Because the presence of matter, for instance, changes the notion of geodesics. So there's a whole...
I say, is it a way of putting matter in this framework to put factors of x and y of that polynomial with Olivier partitionability, maybe? You know,
I don't know.
The way in which you follow the tree is really like that you can read out if you have an externally active edge or something like that.
In the discrete case, you can give sense to that, I guess, but I don't know how to. I don't know how to do it. Otherwise, I would have.
Well, you suggest to put a Potts model on the random surface. Is that
Yes, but instead of just summing over subgraphs, you use partitionability arguments which reduce you to sum over trees, and then it's something like you have a factor y of that, which is 1 plus the factor that you have if you have a loop. If the 2 points in the random tree, in the random Brownian motion, can face each other, and 1 if they meet a moontie maybe or something like that. Of course, it doesn't make sense in the Brownian motion because you can never go out because you will move back.
for probabilists? I mean, can one do the same with matter?
Okay.
Oh, you had a question?
I had this question about matter. That physicists they try to embed the graph into to another simple graph, for example.
Okay.
Easy model.
Mm-hmm.
I wanted to ask you if you had results about.
No, I've not looked at that.
So I think we should thank you again.